Hello my precious friends, I really hope that you are doing great. Welcome to our today's class. It is our 6th lesson on the first topic of Form 4, which is called thin lenses. As usual, let me commence by giving the quote of the day, which states that sometimes you have to fight through the worst moments of your life in order for you to create the best moments of your life. We shall discuss that quote at the end of our class today. So today we are looking at application of the thin lenses, and the first application is what we call a magnifying glass, or in a simple microscope. So in a magnifying glass or in a simple microscope, an object is placed between the principal focus and the optical center of a convex lens. Then the image formed is usually virtual, upright, and magnified. Then in this particular application, we use lenses that have very short focal length. The reason is being so that they produce a high power. Remember, when the power is high, it simply means that the image formed will actually be highly magnified. So remember, the power of the length is given by the reciprocal of the focal length. Therefore, the shorter or the smaller the focal length, the higher the magnifying power of that particular length, and vice versa. So you can see we are having our object placed between F and O. That is, the object is placed between the principal focus and the optical center. Then I can use any two appropriate rays. So the first ray, I'm taking a ray of light through the optical center, will actually pass undeviated. So I simply extend it on the other side. Then a ray of light which is close and parallel to the principal axis will always be refracted through the principal focus. So you can see that on the right hand side, the rays are appearing as though they are diverging away from each other. So that simply means even if we try extending them from the right hand side, these rays will never intersect. But if we try extending them from the left hand side, the rays are appearing to converge at a common point. So this is the point whereby the head of our image will be. Then of course we just plot our image as shown in this particular diagram. So you can clearly see that the image formed is far much magnified as compared to the object. Therefore, the image formed is actually virtual because it is on the same side of the length as the object. So the image is virtual. It is also upright because the object was facing upward. The image is also facing upward. Then the image is highly magnified. So this is what happens in a magnifying glass or in a simple microscope. Next, we look at the compound microscope, which is just a modification of the simple microscope. So it usually has two lenses. That is the objective length, which is the length which is closer to the object. So it is called an objective length because it is usually placed closer to the object. Then we have the eyepiece, also called the ocular. So it is called the eyepiece because this is the length that is placed closer to the eye of that particular observer. So the object to be viewed is usually placed between f0 and 2f0, where f0 is actually the principal focus of the objective length, and 2f0 is simply the center of curvature of the objective length. Remember, if you take focal length times 2, you just get the radius of curvature, which takes you to the center of curvature. So you can see our object is placed between f0 and 2f0 of the objective length. So O simply represents the objective length. Then of course, so that a real inverted and magnified image is formed. So I'll simply use any two appropriate rays to locate the image that is formed. So first of all, I'm using a ray of light which is through the optical center. So you can see that particular ray will always pass undeviated. Then I'm using the second ray, which is a ray of light which is close and parallel to the principal axis. It will always be refracted through the principal focus, that is f0 of the objective length. So this particular ray will always be refracted through f. So you can see they are coming to meet at this particular point. So at the point of intersection of the two rays forms the head of our image of the objective length. Therefore, this is our image of the objective length. You can see that the image is actually inverted because the object was facing upward while the image is facing downwards. The image is also real because it is formed on the opposite side of the objective length as compared to the object. You can also see that the image is somehow magnified. If you compare, for example, the height of this particular image and the height of this object, you realize that this particular image is somehow magnified. So the image is real, inverted, and magnified. Then this image is in front of the eyepiece. So the image is usually formed in front of the eyepiece. So you can see this is our eyepiece or the ocular. this is the focal length of that particular eyepiece. So the image is formed in front of the eyepiece and acts as an object to it. So the eyepiece is adjusted so that the image falls between FE and that is, it falls between FE, that is the focal length of the eyepiece, and the optical center of that particular eyepiece. So you simply use the fine adjustment knob and the coarse adjustment knob of the microscope so that you set such that the first image that is formed, it falls within the focal length of the eyepiece and the optical center of that particular eyepiece, so that on further magnification it will produce a very magnified image. So the image of the objective length will now act as our object of the eyepiece or the ocular. So this image acts as the object of the eyepiece or the ocular. So again, we'll use any two appropriate rays because this is now our object of this particular eyepiece. So I'm going to use a ray of light through the optical center. It passes undeviated, as you can see. Then I'm also going to use a ray of light which is close and parallel to the principal axis. You can see this ray is parallel to the principal axis. Such a ray will always be refracted through the principal focus now of this particular the eyepiece. So from the upper side, you can see the rays are diverging each other. Therefore, even if you continue extending, they will never intersect. But from the lower side, the rays are coming to converge. Therefore, on extrapolation, remember, rays that are behind the lens will always be virtual. That's why you are using the dotted lines here. So you can see this particular ray on extrapolation and this other ray on extrapolation. They are meeting behind the eyepiece, behind the eyepiece. So you can see the point of intersection forms the head of our image. So the image, because the image is on the same side as the object of this particular eyepiece, it means that the image is actually virtual, and that is why we are denoting it with dotted lines as shown in this particular diagram. So you can also see that the final image is very highly magnified, or it is highly magnified as compared to the initial object from the objective length. So you can see the image is formed that is beyond FE. It is formed beyond the principal focus of the eyepiece in this particular case. Then it is on the same side as the object of the eyepiece. That is why it is virtual. So characteristics of the final image that is formed: one is that it is magnified, two is that it is upright. Upright because the object of the eyepiece was facing downward. Also the object of the that is the image of the eyepiece is also facing downward. So in relation to the object of the eyepiece, actually this particular image is upright. But in relation to the initial object, which was from the objective length, the image is actually it is inverted. That is, if you compare with this object, then the image is inverted. It is, of course, it is not real. That is, it is virtual, and of course it is highly magnified. So the eyepiece is adjusted so that, of course, using the fine and the coarse adjustment knobs, so that its image falls between the principal focus of the eyepiece and the ocular. That is between the principal focus of the eyepiece and the objective, that is the optical center of the eyepiece. So this way, the eyepiece acts as a magnifying glass, producing a final image that is greatly magnified. So this final image, which is I33. So that is the I22, which is actually greatly magnified. So if you want to find the total magnification of this particular microscope, you simply take the magnification of the objective length, you multiply by the magnification of the eyepiece. So from our previous classes, we showed that magnification can be given by, that is from the length formula, which was 1 over f is equals 1 over u plus 1 over v. Magnification, if you introduce magnification in that formula, you will get magnification is equals to v over f minus 1. You can just refer from our previous two lessons. We actually derived this particular equation. So the magnification of the objective length is equals to v naught, which is the image distance of the objective length over the focal length of the objective length, then minus 1. So similarly, magnification of the eyepiece is equals to the image distance of the eyepiece over the focal length of the eyepiece, then minus 1. Therefore, total magnification, we just take the magnification of the eyepiece multiplied by the magnification of the objective length. So magnification can be given by, so magnification of the eyepiece is VE over FE minus 1. So the image distance of the eyepiece over focal length of the eyepiece minus 1, then multiplied by magnification of the objective length is simply the image distance of the objective length over focal length of the objective length, then minus 1. But from our previous classes, we did say that magnification can be given by image distance over object distance. Therefore, magnification of the eyepiece will simply be given by the image distance of the eyepiece over the object distance of the eyepiece. Then magnification of the objective length will just be given by the image distance of the objective length over the object distance of the objective length. So any of these three formulas can be used to find the magnification of the compound microscope. So remember, magnification can also be given by height of the image of the objective length over height of the objective length multiplied by, that is, height of the image of the eyepiece over height of the image of the eyepiece multiplied by height of the image of the objective length over height of the object of that particular objective length. That is HI over HO. So you can use those formulas of magnification. You simply find magnification for the objective length, then you multiply by the value of the magnification for the eyepiece for you to get the total magnification of that particular microscope. So let's look at an example involving application of these particular formulas. We look at an example of how an image can be formed in a compound microscope. So it reads that a compound microscope with objective length L1 or focal length 0.8 centimeters. So you can see my focal length of the objective length is 0.8 centimeters, that is F0, and an eyepiece length of focal length 2.5 centimeters. So the eyepiece length, which is L2, has a focal length of 2.5 centimeters. An object O is placed in front of the objective length at a distance U1, which is 1.2 centimeters. So 1.2 centimeters. Then the system forms a final image I2 at the distance of 10 centimeters from the length L2. So you can see our final image is formed at a distance of 10 centimeters from the eyepiece, which is actually the L2. So part A, we are required to determine the distance of separation between L1 and L2. So you can see we let the distance of separation between L1 and L2 to be equal to x, so that when we just find the value of x, we would have answered the question. So F0 represents the focal length of the objective length, which is 0.8. Fe represents the focal length of the eyepiece, which is 2.5 centimeters. U0 represents the object distance of the objective length, which is 1.2 centimeters. Ve represents the image distance of the eyepiece, which is 10 centimeters. Then we are letting the distance between L1 and L2 to be equal to x centimeters. So from the length formula, which is stated that 1 over f is equals to 1 over u plus 1 over v, now for the case of the objective length, if I take 1 over f0, where f0 is the focal length of the objective length, should be equal to 1 over u0, which is the object distance of the objective length, plus 1 over v0, which is the image distance of the objective length. So I'll just substitute the values so that I get the unknown. So 1 over f0 is 0.8 centimeters. So 1 over 0.8 centimeters is equals to u0 is actually 1.2 centimeters, then plus 1 over v0, of course, whereby v0 is simply the image distance of the objective length. So I'll simply take 1 over 1.2 towards the left hand side so that it becomes a negative. So I'll have 1 over 0.8 minus 1 over 1.2 being equal to 1 over v0. So of course, if you take 1 over 0.8 minus 1 over 1.2, you just obtain 5 over 12, which is equals to 1 over v0. So if I do cross multiplication, I'll have simply a v0 times 5 being equal to 1 by 12, which will just give me v0 being equal to 12 over 5. Or you can as well just take reciprocals on both sides. So you'll have v0 over 1, which is just v0 being equal to 12 over 5. So on simplification, 12 divided by 5, you'll obtain 2.4 centimeters. So this is the v0. That is the image distance of the objective length. So this is actually this distance here, the distance from this particular objective length up to where our image is formed. So this is the image that is formed by the objective length. So the distance from here up to the objective length, that is 2.4 centimeters. Then we can clearly see that if you want to find UE, which is the object distance of the eyepiece, we'll simply have x minus 2.4. Because if the distance from the objective length up to where the image of that particular objective length is formed, that is at this particular point, if that distance is 2.4 and the distance from L1 to L2 is actually x, it simply means that the remaining distance, which is the distance from our image up to the eyepiece, will actually be equal to x minus the distance from the image that is formed measured from the objective length. Therefore, the object distance, that is the distance from here up to the eyepiece, this particular small distance here, will simply be given by x minus 2.4 centimeters. Then I replace in the formula for the length formula, but now for the case of the eyepiece, whereby we'll simply say 1 over Fe must be equal to 1 over Ue plus 1 over Ve. Of course, where Fe represents the focal length of the eyepiece, Ue represents the object distance of the eyepiece, then Ve represents the image distance of the eyepiece. So 1 over focal length of the eyepiece, of course, the focal length of the eyepiece I was given as 2.5 centimeters. Therefore, 1 over 2.5 must be equal to 1 over the UE. We have stated the object distance of our, that is the object distance of the eyepiece is actually x minus 2.4. So x minus 2.4, then over 1 over VE, where VE is the image distance of the eyepiece. So image distance we are given as 10 centimeters, so over 10 centimeters. So I'll simply collect the like terms. So I'll take 1 over 10 towards the left hand side, so that I have 1 over 2.5 minus 1 over 10 being equal to 1 over x minus 2.4. So if you take 1 over 2.5 minus 1 over 10, you simply obtain 3 over 10. So if you simplify this particular equation, if you just cross multiply, you'll have 3 multiplying by x minus 2.4, this equation here. Then of course 10 times 1, you just obtain 10. So if you simplify this equation by first of all opening the bracket, so it will be 3x minus 3 multiplied by negative 2.4. So if you solve this equation, you will find your value of x being equal to 5.733 centimeters. That is correct to 4 significant figures. So that is the value of x. So remember, the question wanted us to find the distance of separation between L1 and L2, and we related x to be equal to the distance of separation between L1 and L2. Therefore, the distance of separation between L1 and L2, which is equal to x, will be equal to 5.733 centimeters. Then part B, they want us to find the magnifying power of the microscope. We have just stated from our previous slide that the magnification of the total magnification of the microscope will be given by the magnification of the first of the eyepiece of the objective length multiplied by the magnification of the eyepiece. Then we stated that magnification can be given by this formula. So total magnification will be equal to VE over FE minus 1. That is the image distance of the eyepiece over the focal length of the eyepiece minus 1 multiplied by the magnification of the objective length, which can be given by the image distance of the objective length over focal length of the objective length, then minus 1. Remember, you can as well use just the value of magnification ME multiplied by MO. You can also use VE over UE, then multiplied by VO over UO. So you simply find the magnification of the first length, that is the of the eyepiece, then you multiply by the magnification of the, that is the objective length. So actually the values that you have will determine the formulas that you use. For example, in this case, I'm already given VE from the question. I'm also given FE from the question. Then of course minus 1. I'm also given VO. We have already computed the value of VO as 2.4 centimeters. We also have the value of FO, that is the focal length of the objective length, which we are given as 0.8 centimeters. So if I substitute, I'll have VE is actually 10, so 10 centimeters over FE is actually 2.5 centimeters, then minus 1, then I multiplied by VO is 2.4 centimeters as computed here, then over FO is actually the focal length of the objective length, which was 0.8, then minus 1. So 10 over 2.5 minus 1, you just obtain 3, then 2.4 over 0.8, then minus 1, you just obtain 2. Therefore, the total magnification is 3 times 2, which gives you 6. So this one simply means that the magnification of the eyepiece is 3 and the magnification of the objective length is actually 2. Therefore, the total magnification will just be 3 multiplied by 2, which is equals to 6. Again, remember, magnification is a ratio, therefore it does not have the units. Next. And lastly, I have an exercise that I recommend you should try at your own free time to gauge the understanding of the examples and the concepts that you have just learned. Of course, if you have any challenges in handling any of the questions, feel free to drop a comment specifying the question that you need help in. And as usual, I'm always here to try and help where possible. So we've come to the end of our class today, but we need to discuss the quote of the day. The quote of the day stated that sometimes you have to fight through the worst moments of your life in order for you to create the best moments of your life. So the quote is cautioning us that not every season of our life will be smooth. Some seasons of our life are meant to teach us very important lessons that will be applicable in our future seasons of life. Therefore, do not regret about your past. Instead, embrace it and use it as a stepping stone to your future, because very tough seasons are usually accompanied with very important lessons that you needed to learn, and you needed in order to improve your mental strength to be ready for the next season of your life. Therefore, embrace every season, pick all the memories, pick all the lessons, and apply them in your future seasons. And lastly, recall that not every challenge comes with an intention of crushing you. Some challenges are there to just harden you and to teach you important lessons about life. Thank you very much for accompanying me until the end of this particular lesson. I do not take it for granted. In case you are new to the channel, kindly hit the subscription button and also turn on the notification bell so that whenever I upload a new video, you'll get notified. Thank you for the continued support. Thank you for your positive comments. I really, really appreciate. If you know anyone that you honestly think could benefit from this content, kindly share my link to them or just refer them to Kind Tuition Academy. Until next time, this is Kind Tuition Academy. Thank you very much.